So far this chapter, we've looked at two different mechanisms for substitution reactions and two different mechanisms for elimination reactions. In this video, we're going to look more specifically about what types of reagents and substrates favor these different types of mechanisms. So we've seen that a lot of different factors can affect what products are formed. We've seen that the substrate, the reagent, and the solvent all play an important role. In many cases, we'll get a mixture of both substitution and elimination products, and so we have to know how to predict all the different products that will be formed, and we need to be able to predict which ones will be the major products and which ones will be the minor products. Now, while it is true that we very often get a mixture of products, sometimes the conditions will favor forming just a single product. So to successfully predict the products from a given set of reagents, I think it's helpful if we kind of break it down into a number of different steps, and we'll look at each one of these individually. So we want to see how the reagent is going to affect the reaction. Then we want to analyze the substrate, and then finally we'll consider any regiochemical or stereochemical requirements that the reaction may have. All right, I think the first thing to do is see how the reagent will promote the various mechanisms. And so the reagents that we've used in this chapter are either nucleophiles, bases, or both. And we've seen that SN2 reactions are favored by strong nucleophiles, E2 reactions are favored by strong bases, and then SN1 reactions result when we have a weak nucleophile, and E1 reactions result when we have a weak base. And so I think this set of categories isn't hard and fast. There are some reagents that will sort of fall in between, but I think it's helpful to sort of think about our reagents in terms of these different categories. So we can have something that is a strong base and at the same time a weak nucleophile, and in that case, E2 reactions will be favored. If we have a reagent that's a strong base and a strong nucleophile, then that will favor SN2 and E2 reactions. If something is a weak base and a strong nucleophile, we'll see SN1 and SN2 reactions. And if something is both a weak base and a weak nucleophile, then we'll have SN1 and E1 reactions. I think we've seen a lot of these reagents before. The one case where that might not be true is examples of things that are strong bases and weak nucleophiles. And so I have the next slide, we'll look more at what these different compounds are. And so I think we want to try to get away from just memorizing where these reagents will fall and try to get an idea of why they are where they are. So these are all strong bases and strong nucleophiles. If you notice, right, they all have negative charges. In the case of something that is a weak base and a strong nucleophile, again, we tend to have negative charges, and we also tend to have things that, even when they have negative charges, they're fairly large and polarizable. And that means that the negative charge is stabilized, and so they're relatively weak bases, right? The more stable the base is, the weaker it is, right? Where in this case, things are both strong bases and strong nucleophiles, right? The negative charge is on the oxygen, which is relatively small, and so that base is not particularly stable, meaning it's a reactive or a strong base. And then when we have things like water and alcohols, these are weak bases and weak nucleophiles. So in that first category, we had a couple of acronyms. We had DBN and DBU. And so these nitrogen-containing compounds are strong bases and weak nucleophiles. And you can see, based on their names, you can see why we like to use these abbreviations. But when you see these reagents, these nitrogen atoms, when they are protonated, they're going to be resonance stabilized, and so that makes them willingly able to be protonated, making them strong bases even though they're neutral. Another example of a strong base and a weak nucleophile is NaH, right? This is an example of a hydride, right? And so this hydrogen actually has a negative charge where the sodium has a positive charge, and so its negative charge makes it a base, but because hydrogen is so tiny, it doesn't make a strong nucleophile. So once we've determined which mechanism is favored by our reagent, we then want to take a look at our substrate. So in the case of a strong base and a weak nucleophile, we only see the E2 mechanism, regardless of whether the substrate is primary, secondary, or tertiary. If we have something that is both a strong base and a strong nucleophile, then we're going to get a mixture of SN2 and E2 mechanisms. Remember that the reactivity of a substrate in an SN2 process goes from primary being the fastest, and then as we become more sterically hindered when we go from secondary to tertiary, the SN2 reaction slows down. So with a primary substrate, when we have both a strong base and a strong nucleophile, we'll have mostly SN2 with some E2 product. By the time we get to a secondary substrate, the E2 mechanism is the major product and the SN2 mechanism is the minor product. And when we get to a tertiary substrate, all we see is E2. Similarly, when we have a weak base and a strong nucleophile, we're going to get a mixture of SN2 and SN1 mechanisms or products. In the case of the primary, we get all SN2. Because again, right, the reactivity of the substrate for SN2 goes primary is the most reactive, it gets less reactive as we go to secondary, and less reactive still. In fact, oftentimes we don't see a reaction when it's tertiary. And so for both secondary and primary substrates with a weak base and a strong nucleophile, we see the SN2 mechanism. When we have a tertiary alkyl halide, we see the SN1 mechanism, because now the SN2 process is too slow, and that tertiary alkyl halide will give us a tertiary carbocation intermediate, which will be particularly stable, favoring the SN1 mechanism. When we have a weak base and a weak nucleophile, we generally don't see a reaction with primary or secondary substrates because that carbocation intermediate is not very stable. However, if we have a tertiary substrate, then we tend to see a mixture of both SN1 and E1. Okay, so by analyzing the reagent and the substrate, we can determine which mechanisms are going to be favored, and so then we want to be able to draw all possible regio and stereoisomers, and then choose the major product using the guidelines that we've learned. And so let's take a look at each one of the mechanisms and review the regiochemical and the stereochemical requirements. So for SN2, as far as regiochemistry goes, right, the nucleophile attacks the alpha position where the leaving group is connected. So there's really only one possible regiochemical outcome. As far as the stereochemistry goes, we know that for SN2, they proceed with inversion of configuration. So if we started out with R, then we'll have the S as our product, and vice versa. Okay, so for the E2 mechanism, there's a little bit more going on. It's important to remember the requirement that the beta hydrogen that is part of the elimination must be anti-periplanar to the leaving group. And this is most important when both the alpha carbon and beta carbons are chiral, because in that case, we'll only get one stereoisomer. We won't get both E and Z, and so we have to be able to rotate around those bonds to put the beta hydrogen and the leaving group in an anti-periplanar position to see which stereoisomer we're going to get. We also have to consider the regiochemistry. So remember that the Zaitsev product, or the one that's more highly substituted, is generally favored over the Hofmann product, which is less substituted. That is the case unless we're using a sterically hindered base like tert-butoxy, in which case a sterically hindered base will favor the Hofmann product. For the stereochemistry, remember that the E2 reaction is stereoselective. Usually the trans disubstituted alkene will be favored over its cis counterpart, or in general, even if we can't use the cis and trans labels, right, we want the big, bulky, sterically hindered groups to be on opposite sides of the double bond. The process is also stereospecific, and so that's what I mentioned on the beginning of this slide, right? We need to be sure that the hydrogen on the beta position is anti-periplanar to the leaving group. Okay, the regiochemistry of SN1 reactions is fairly similar to SN2 in that the nucleophile attacks the carbocation, and the carbocation is generally on the carbon that lost the leaving group, but it's a little bit more complicated than in SN2 because carbocation rearrangement is possible. And so it is possible that the carbocation may have moved, in which case the nucleophile can attack multiple possible positions. When we consider the stereochemistry, the nucleophile replaces the leaving group, and we tend to get both retention of configuration and inversion of configuration due to the formation of ion pairs between the leaving group and the carbocation. Usually we get a little bit more of the product that results from the inversion of configuration and a backside attack. Okay, for the E1 mechanism, just like in SN1, we first form a carbocation, and so we have to be careful that we can also have carbocation rearrangement in the E1 mechanism. Now, E1 is a little bit simpler than E2 in that the Zaitsev, or the more highly substituted alkene, is always favored over the Hofmann product. And the process is also stereoselective, so when applicable, right, the trans disubstitute alkene will be favored over the cis disubstitute alkene, or more generally, right, it's going to favor the product where the bulky groups are on opposite sides of the double bond. All right, so let's take a look at an example. We want to predict all the products that would result from the following reaction, and we want to label the major product. So first, we'll analyze the reagent. So we've got sodium hydroxide, right, or really what we're interested here is OH minus. So OH minus falls into the category of being both a strong base and a strong nucleophile. And so that's going to tend to favor both SN2 and E2. When we look at the substrate, we have a secondary alkyl halide. And so if we go back to the chart, or we think about that chart, if we had a primary alkyl halide, that's going to favor SN2, and the SN2 is going to be our major product. In the case of a secondary alkyl halide, we're again going to get a mixture of SN2 and E2, but in this case, the E2 is going to be the major product. If this had been a tertiary alkyl halide, then we only would have seen the E2 mechanism. But in this case, we're going to see both SN2 and E2, but E2 is going to be the major mechanism. Okay, so now we want to consider the regio and stereochemical requirements. And let's do SN2 first, and we'll do E2 on the next slide. So the regiochemistry part of the SN2 mechanism is fairly simple, right? The OH is going to attack the carbon that has the leaving group. For the stereochemistry requirement, remember the SN2 proceeds by backside attack and gives inversion of configuration. And so wherever we have wedges, we're going to switch those to dashes. And so our one SN2 product is going to be this. All right, let's consider E2 on the next slide. Okay, so to determine the E2 products, I want to first find all my beta hydrogens. So I think I have a methyl group here, and then I have two hydrogens up there. So I can either get a double bond here or a double bond here. At this point, it's good to see, are we going to have a situation where only one stereoisomer is going to be produced? I think that's not the case. While the alpha carbon is chiral, neither of the carbons containing hydrogens that I'm going to eliminate are chiral. They both have two or more hydrogens, and so if there are going to be stereoisomers, I'll be able to get both of them. So first, let's consider the products that we get by putting a double bond here. All right. Now, we also want to look and see, do we have any E and Z isomers in this case, right? And now, because I have two hydrogens coming off here, it's not stereoisomeric, and so there's only one product by putting a double bond here. Now let's consider the products I could get from putting a double bond here. Okay, and in this case, I think this is a stereoisomer, right? In this case, we have the Z configuration, and so the E configuration is also possible. And so I think there are going to be three E2 products of this particular reaction. And so let's go on to the next slide, and we'll add in the SN2 product and determine which of the different products is our major product. Okay, so we have our SN2 product, and then our two E and Z isomers. And then for this one, I've just rotated around this double bond, but this is the same one as where the double bond was here. We just rotated around this single bond. And so we said before that due to the fact that we have a strong base and a strong nucleophile, that's why we have both E2 and SN2 products. But because we have a secondary substrate, the E2 is going to be the major mechanism. And so I know that this is going to be a minor product. And then when I compare the three different E2 products, these two are di-substituted, whereas this one is mono-substituted. So I know the one on the far right is also going to be a minor product. And then when I compare these two, the E isomer, where the bulky groups are on the opposite sides of the double bond, is going to be favored over the Z isomer, where both bulky groups are on the same side of the double bond. So this is going to be our major product, and this is another minor product.